All right, didn't get
Thank
any
you.
questions in advance, so if you've got any questions, please post them to the chat. I'm here, but I'm getting work done, and I'm assuming that you don't want to listen to me typing away at the computer, updating some study guides. So if you have a question, put it up in the chat. I have it. Keep in mind there's about a minute to 2 minute lag. I will say, for those of you in the Friday lab, it's looking like there's probably going to be snow this Friday. If there is, you'll get an announcement. We still got that review to do, so odds are we're going to do something through Teams. But again, just particularly with the Friday 251 section, and those of you planning on going to office hours on Friday, do keep an eye out for the weather. It is looking like most likely the school will be canceled that day. All right, so I'm here. If you got questions, please post them. So, question just got asked: Wolf Kishner, why doesn't it reduce other groups? It does. Actually, it'll. I think it's the acid unstable ones that will reduce. So something like a ketone will react with acids. It'll accept a proton. I'm not sure if the Wolf Kishner mechanism has been worked out yet, but yeah, if you go through basically Wikipedia stubs or textbooks that actually discuss Wolf Kishner reductions, they'll say will affect it will leave certain groups alone, but other groups it will actually reduce. And so when it comes to Wolf Kishner, it's softer than a Clemmensen reduction, that mercury zinc amalgam with HCl. The mercury zinc amalgam with HCl, that will pretty much reduce anything that has a ketone in it. But yeah, to answer your question, it will actually reduce other groups. We're going to stick to simple examples where the ketone is pretty much the only functional group there. But this is kind of the issue with, that's why you had the three different options. That's why you had the Clemmensen, the Wolff-Kishner, and the Mozingo reductions, is that if you happen to have these other functional groups available, you do actually kind of have to go look up which ones are affected by these particular types of reductions. And again, we're not going to go into that level of depth in this course. This is not meant to be like a graduate course where you would be designing like long, complicated syntheses, a lot of questionable function groups. It's more just kind of there to give you familiarity with the fact that, yeah, if you do have a carbonyl group adjacent to a phenyl ring, there are three options for getting rid of it. There are probably several more if you go cite the literature, each trying to address a functional group that you're trying to protect. Be aware that those options are out there. Be kind of aware of what they can and can't do. So your Clemmensen is the most aggressive, which means it's probably going to reduce a whole bunch of other functional groups. Your Mozingo is the least aggressive. It's also going to take the longest, which is why it doesn't really affect as many other functional groups. But you're not going to be given any esoteric examples where like one's not possible whereas the other one is, if that's really what you're asking. So you're not going to get a situation where one of those three reductions is the correct answer. All three are possible for the type of functional groups you're working with. But again, they do react. That's why we have the three different types of reductions. It does kind of say in the notes like this one's better if you've got these groups, this one's better if you've got these groups. But they definitely all have potentials for reducing and even eliminating other functional groups that are in your rings. So this is why the field of organic chemistry exists, is to kind of get around these synthetic problems. So should you memorize the different reagents? I would say you probably only need to memorize the Clemmensen reduction. That's the easiest. That's the zinc mercury amalgam with HCl. The Clemmensen and the Mozingo, I don't necessarily know off the top of my head. I know that there's a lot of reagents that go into those. So I think with like Wolff-Kishner, it's H2 on Raney nickel with that diamine that's in it. And then I think for the Mozingo, there's a thiol that's in it. But again, we're not going to deal with scenarios where like one is used over the other. Like you can definitely conceive of examples where you would never do a Clemmensen reduction because it's too aggressive. You need to switch to like a Mozingo reduction. We're not going to worry with those. But as long as you know one way to pick off a ketone adjacent to the benzene ring, that's the more important thing to know, that you kind of do have that synthetic tools box for like clipping off ketone groups. And this is going to come up when we start talking about aldehydes and ketones in the next chapter, like how do we change a ketone to what we want it to be? How do we change an aldehyde to what we want it to be? But yeah, you don't have to memorize all three. Just pick the one. And again, I think the Clemmensen is the easiest to memorize, just so you kind of have that in your synthetic toolbox, but also have that knowledge in the back of your head that, yeah, Clemmensen reduction doesn't work for everything. It will definitely reduce off groups that you don't want to reduce. We're just not going to deal with those. Again, that's more of a graduate course where you would cover those types of things. So the next question got asked, in the solution key it says that you can run the reaction in two different orders. One would be faster than the other. How do you choose what you do? You would do the one that runs faster, and it's just pure practicality. Why take a reaction that takes longer and longer and longer when you can just run the shorter one and be done with it? So generally speaking, we're going to try to go for reactions that are faster. So going back to your earlier question about the three different types of reduction, if you can run a Clemmensen reduction, you're going to run the Clemmensen reduction because it goes fast. Something like a Mazinga reduction, you're talking in like 8 to 9 hours to get a decent yield off of a simple ketone reduction. Your Clemmensen reduction is probably going to be closer to instantaneous, maybe 15 to 20 minutes. It's pretty much just practicality. We want the reaction to go as fast as it can because we don't want to like waste our time waiting for things to run. But that said, if you do end up with a situation where the fast reaction has poor selectivity, you have to weigh risk to reward. So if you have an issue of like your faster method creates a lot of side products, but those side products are easy to like reprocess back into your desired product, you'll probably go with the faster route. But if you find that the faster route produces a lot of undesired side products and the product you're trying to isolate is super expensive, you're probably going to go with the slow and steady one that actually gives you a better yield. And this is more into reaction engineering when we start talking about the feasibility of reactions. If you have a reaction that takes like months to run, you're probably not going to be running that reaction because it takes forever for it to get to completion. Like you would have to have something that's super high value to justify such a time. So something like wine. Wine takes 2 years to produce. It's a slow reaction, but it's pretty much guaranteed to give really good yields. And it produces a high value product. But there are other things like if you're trying, there are definitely reactions that if you run very slowly, you get good selectivity, but they're not worth the cost. Like what it would cost for you to run that reaction for so long would not offset the cost of making the chemical. So again, we're not at the point where we're going to like favor like what's the faster mechanism, what's the faster reaction of all possibles. You're not graduate students, you wouldn't have a background with all these different reactions. Also, full fun fact, typically what you do in research, there is a database called the Novel Database, KNOVELL. The Novel Database is a collection of all scientific papers in all journals. You would actually search that for the reaction you're looking for, and you would look at the papers to see how they did it, the feasibility of what they did, the types of yields they got, and if that's what you want to do. So no one knows all of these reactions off the top of their head. People tend to typically specialize. But again, this is kind of organic chemistry course is getting you a flavor of these types of reactions. And we're not going to worry about like, well, did you do it the fastest way? What we're going to do more importantly is did it work? So did what you write actually make sense in terms of producing the product you were trying to produce? If you have a slow route but it works, that's the right answer. If you have a fast route that doesn't work, that's the wrong answer. All right, next question. For acylation, does it only apply to primary? Yes, because there's no way to do an acyl chloride that isn't a primary. So if you look at your acyl complex, your acyl is always something RCl. So there's no way to put a chlorine on this carbon, and there's no way to even have a ketone on a tertiary. So your secondary and tertiary, these are just handled by doing the straight chlorides. You're not likely to get rearrangement, but you definitely can with these. Oops, 2D bonds. But yeah, the acyl here is only going to apply to the primary because that's the only way to have a acyl chloride is to have it hanging off the end of the reagent. So for secondary and tertiary, we're pretty much going to exclusively work with the alkyl chlorides. You can get some complications with the secondaries if you have something like this, but generally speaking, they should be pretty good for doing that binding reaction. But as far as how you would stop something like this from rearranging, it's probably actually a very good synthetic question. My best guess is that there are probably, you'd probably put a blocking group on there, or, because there's no good way to attach that. Honestly, you would probably try just to stick to something like this. Do the alkylation here, because even if you get resonance here, you're going to get the carbocation here, and then you're going to follow after you do your acylation. You're just going to reduce with hydrogen. So my best guess is that if you want to attach a secondary where there's a potential rearrangement, find a starting alkane, so find a starting hydrocarbon that you can work with, that you can kind of like keep that rearrangement from happening, or if you do get rearrangement, you basically get nothing out of that rearrangement. Like it doesn't change anything about your molecule. But again, the reason we have to use acylation is because if we did the primary, we would definitely get rearrangement. Anything's better than a primary. But there are exceptions to this. So if you had methyl chloride, CH3Cl, you can do that directly because there's no way for that to rearrange. But if you had like an ethyl, or if you had an ethyl group, you do ethyl chloride. That works just fine because the ethyl chloride's got that carbocation has nowhere to go. But when you get something like a propyl group, the CH3, that CH2 group between the two CH2 groups, that'll definitely undergo rearrangement. Right, so next question was how you add groups to benzene rings, and particularly if you have more, so you're trying to do a retrosynthesis. So you're starting with something, and you want to go to two groups. And we're typically going to have the groups in one of two positions, either the para ortho meta position, or we're either going to have the meta position or the para position. So let's say we're adding two groups here. And let's see what colored pens I have. Green. Let's say we have two groups. We're going to add an X group. Oh, that pen's dead. Guess we'll be going with red. So we're going to add a red group and a black group. I'll tell you what, for right now we're going to find X as an ortho para director, and the red one as, we'll start with a meta director. So we want to know which one we want to add first. So what we're going to do is we're going to consider what happens if we add them in different orders. Now, in benzene ring, all 6 positions are equivalent until we add something to the ring. At that point, that's where we get direction. So let's say we add the ortho para director to this one, and we add the meta director to this one. Now, if you look at what gets added next, the ortho para director is going to say whatever gets added next is going to get added to these 2 positions, whereas the meta director is going to add something there. So whatever we add next, in this case the red X, is going to get added to either here or here, most likely the bottom group. Whereas when we start with this one, we're going to add our next group in the meta position. So depending on what we add first will dictate where something ends up next. Come on. There we go. So then we look at what we want to produce. If we want to produce the para product, we would add the ortho para director first. If we want to produce the meta product, we'd add the meta director first, and that would direct their next group meta. Now, what happens if you have 3 groups? So with 3 groups, there's a lot that goes on. I really wish I had a different colored pen. Seriously, what happened to my blue pen? So let's say I have 3 groups. A, B, and C. And this is a hypothetical molecule, so we're not going to, I'm going to make a guess as to what they could be, but again, we're going to have to accept that maybe this example won't work. But let's say that A is an ortho para director. So what I'm going to do is I'm going to put a little black circle for where A would force things to go. And let's say that B is also an ortho para director. So B here, we're going to give a little star. So B is going to put, it's an ortho para director, it's going to put something here, here, and here. And let's say C here is a meta director. So C, I'm going to give red pen. So C is going to put a group here and here. So what we're looking for in this situation is the odd man out, the one person that doesn't seem to have a directing group that puts them where they're supposed to go. So if you looked at A could be put there if B was already on the ring, because B is an ortho para director and A is sitting on the ortho position. If we look at B, B could be here because we've got the A group forcing it, A group favoring it because this would be ortho to A, and C forcing it because C would be meta. If we look at C, C could be here if B got added first. So we start looking at it in terms of what would have to come first. So if A was being added, B would have to come first. So B would have to come before A. To add B, either C would have to come first or A would have to come first. And to add C, so C would only get there if A was being added first. So the question is, do any of these like tether together to give us what we want? So do we have, in order to add B, we'd have to have A coming first. Oops, it should be there. So honestly, these could be added in either, what this is saying, they can be added in either order. They would both give each other the same direction. But if we add C first, we'll get B, because none of these have C coming first. So this would have to be the first step, because adding C first is going to drive the B group into that desired position. Again, it doesn't matter where we put it on the ring because it's got all that symmetry to it. So the reason why I'm going to add C first is it's the only situation, there's only one scenario where I can add this in such a way that, because basically C is not getting directed by anything. C could be added to the ring if we have A first, and then, but the only way to add A is if we have B first, and these kind of, we get into this weird loop. But if we add C first, we get B added to the meta position. So then we add B, and then we can add A, and that should give us this. Now, what if we wanted to add A first? So if we added A first, then we added C. So if we add, make sure I got enough space. So if I add A first, dig up here, and then I would add C, and that would put C in the, you can kind of sort of see that, around our board. And if we add C, sorry, up here, C down here, and then when we add B, get that? I know the C is kind of trailing off the end of the screen there. So there's actually two synthetic routes you could do here, and then you would just kind of sit back and say to yourself, okay, what's more likely to occur? So, or what would make more sense? I would say actually this second route works better. So A is most likely going to put C in the para position, and then when you add B, well actually no, neither of these are particularly like guaranteed syntheses. You'd have to look at the strength of A and C. If C is a really good meta director, I would go with this. If A is a really good if B is a really good ortho para director, I would go with this route. But hopefully you can kind of see that line of reasoning is like you'd ask yourself what would have to come before this group. You want to add groups A, B, and C to the ring, and based on their positions in the rings, what could come first to direct into that position. In an ideal scenario, you end up with an odd man out. Basically what happens is that if you look at one of those groups, none of the other things on the ring would ever put it in that position. That tells you it comes first because there's nothing you can put on the ring that would force it into that position. It had to be there first because if it wasn't there first, all the other groups would force it to a different position. Can't think of anything off the top of my head, but this is kind of what you would work through is say, okay, what came first to get us into these positions by looking at where each of these groups direct. And three substituents is really hard to work with because you can sometimes get competing effects. And the notes do talk about this where if you're fortunate with the example you're given, I had to make this one off the top of my head, but if you were fortunate with the example you were given, you're probably going to notice that if you add two groups to the ring, there's only one position where the next group can be added, and that's where you want to add the next group. So you can start working your way backwards to see what had to get added first. You can definitely end up with ambiguous situations. So this is an example where A and C reinforce each other. Well, actually, A and C don't reinforce each other. A and C are actually working against each other. So A is going to direct. Actually, no. Here A and C are reinforcing. Oh, if you had B and C are at odds because B is adding to these two positions and C is adding to these two positions. So B would have to be the better electron donor to get A to add in this position. But if C was a really good electron withdrawal or a very good meta director, it would push the A group here. So again, working backwards, figure out, hopefully you can find an odd man out that if you start tweezing out where all these groups get added, you're going to notice there's kind of a blank spot, like nothing adds to this position. If you have a group that's on a position in the ring that none of the other groups would ever direct there, that's going to be the first group to get added. If you have a situation like I drew up here with the hypothetical where they all can direct each other to those positions, that's when you would start coming up with these hypotheticals and saying, okay, if I added this group first, what would I add next? What would I add next? And what's most likely to get me to where I want to go in terms of the synthesis? So a question I just got asked: why is ortho hindered, steric hindered, and para more para, and meta? So I'm guessing what the question is. We talk about ortho para directors, but typically it's always added in the para position. It's because whatever group is typically a ortho para director, the ortho group is sterically hindered. So an easy way to see this is if you look at the CH3 group. So a CH3 group prefers to direct ortho para, but almost always we get interaction at the para position. Why is this? So if we look at the CH3 group, it's not just CH3. It's hydrogen sticking out in space. And these do occupy some space above the benzene ring as I have it drawn. So if you want to add to the para position, the only thing that's down here is a hydrogen. That's the only thing you really have to push out of the way to get your group added to it. But if you want to add to the ortho position, anything that gets added here is going to start bumping up against these H groups. Now for CH3, this is a pretty subtle effect, but as you start getting to bigger and bigger groups, you're going to start seeing this effect more and more and more, where basically it really has to like work its way underneath that directing group in order to add to the ortho position, whereas in the para position, it's pretty free to do it. Now, you can also make a separate argument to say that this has to do with resonance. So typically, if you have an ortho para director, these are resonance stabilized, and it takes time for this resonance bond to work through the molecule. I'm not a huge fan of that argument. Resonance is not as straightforward as it looks for in Lewis structure. You typically have an average of structures. It's not clear if they're truly interconverting or not. So I would say the steric hindrance is the bigger thing here. But again, keep in mind that even though we may draw them as simple like lines, there are hydrogens. There are a lot of groups that are there pushing at the groups against it. So why can't you look at the last group and then add group 3? Because it depends on their relative strengths. You really do want to consider both, particularly if the two groups are at odds with each other. So in an ideal scenario, so let's say that this is an ortho para director. So CH3 is going to direct here, here, and here. And let's say that we've got like a nitro group here, NO2. And your nitro group is going to direct here and here. So this is a nice scenario where these both are reinforcing each other and they're directing everything to the same position. But let's say now they're at odds with each other. So we have our CH3 group and we have our nitro group. And our CH3 group is an ortho para director. But, where are you at? There you are. Our nitro group is a meta director. So our nitro is going to force groups here and here. These two groups do not agree with each other. And so in the situation on the right, we basically get that the only where it depends on whether CH3 is a better ortho para director or if nitro is a better meta director. And that's why we have to consider both, is that they're both affecting this ring. This is making this position very favorable for bonding, but this is making these three positions better for bonding. Now, nitro is a strong electron withdrawing group. It's a very good at meta director. So most likely whatever you add next is getting tacked on here. But that's why we have to consider both groups when we talk about it, is that they can have competing effects. And if they do have competing effects, it's a matter of not who got added last, but who's better at directing. So it doesn't matter who you add in terms of a nitro and CH3 group. The molecule doesn't have a memory of that. What it knows is what it currently has, which is the two groups that are attached to it. And the group that's better at directing is going to be the one that dictates where attachments get made. A Schiff base. Not quite sure your question. Hold on. So why is the orthosteric hindered more para and meta for shift? So I'm looking at the shift base. And so the reason why the shift base is more sterically hindered than para is because there are functional groups at both the para positions. It's a massive compound. I'm not going to draw it out. But definitely, your para position, you have another benzene ring, and so that's just going to block everything out. You're pretty much looking at pretty much the ortho positions being because they're next to that bridging oxygen, are most likely to be less sterically hindered. But the other thing is I'm looking at the shift base, and the shift base, so this is one example of the shift. So the one example that's being given in Wikipedia of a shift base is a very large, bulky aromatic. But for shift bases in general, it's the structure R1, R2, C double bond in R. This is not going to have ortho-para directing because there's no benzene rings. So R3 can be an alkyl or aryl group. To be honest with you, shift bases are a bit outside my expertise. But if your group, yeah, you need to send me an example of what you're asking about. Page 21 and 22. Let me get to it. I need to download it first. Okay, give me just a minute. Yes, so if you had, so all these are just starting reactions of benzene, the methyl is left off intentionally to kind of keep it simple. But definitely with all those, if you had a methyl group present, you would have to, yes, it would basically add everything ortho-para, with most of them being added to the para position. And then when it asks you which way it goes, if you were talking about relative to the methyl group, you'd have to see the effects of the group that you just added. If you added another alkyl group, it would activate the other four positions, so you really wouldn't have favorability. But if you added like a meta director, like an NO2 group or a ketone group, that would direct it towards the ortho position relative to that methyl group. You're welcome. All right, so for Friedel's crafts, do you always have to use carboxylic acid, SO2 to convert? Generally speaking, if you're making the acyl chloride from scratch, yes, you're going to take the carboxylic acid, react it with thionyl chloride, and that will convert you to the acyl chloride, which you'll subsequently react to your compound. That said, ideally, you just go ahead and buy the compound pure, because that thionyl chloride is going to produce a product that you're going to have to separate out. You also have to make sure that you've isolated out your carboxylic acids. So, short answer is if you are starting with a carboxylic acid, yes, you'll need to work with a thionyl chloride. In practice, you would generally kind of like buy the thionyl chloride straight and use that so somebody else has to take care of the purification steps. All right, last question before I head out. If you're writing stuff for synthesis, you have to include that only if it's giving you the carboxylic acid as the starting compound. So if you're given a synthesis saying starting with these two molecules, convert them to an alkylated or acylated benzyl ring, and you're given a carboxylic acid, then yes, you'd use the thionyl chloride. Otherwise, it's just a matter of what you're given. If you're not given the acyl chloride, you don't have to start with the carboxylic acid. You can just start with the acyl chloride. So again, it's the context of the question, but like if you are given a carboxylic acid and you want to do a Friedelsgraph acylation, you're going to have to use thionyl chloride to get there, but you don't have to make it hard on yourself. If you're given an acyl chloride, just work with the acyl chloride straight. All right. So what's checking out the weather? It does look like Friday is probably going to snow. So for those of you in the 251 section, you are probably not going to have class Friday. I'll send out a preemptive announcement probably tomorrow or Thursday to let you know what we're doing to make up the missed time. But other than that, I will see a lot of y'all tomorrow.